Next type of beam is overhanging beam. If one end of beam is overhang and other end is supported, then such a beam is called as overhanging beam. Sometimes both ends of beams will be overhang and supports are connected at the middle portion of beam. So example of such a beam will be as overhanging beam. So this is an example of singly overhanging beam as only one portion of beam is overhang. And this is an example for doubly overhanging beam as both ends of beam are overhang. Free body diagram for this beam can be drawn as for fixed support there is a number of generation of two constant reaction as AX and AY. For roller support, one constant reaction will be generated. For this beam also same, we can draw free body diagram as AX. Here is a reaction AY and here is a reaction BY. So this is the free body diagram for overhanging beam. Next type of beam is continuous beam. If beam is having number of support more than 2, then such a beam is called as continuous beam. Continuous beam is normally provided for the longer supports, longer spans. So this is a one example of continuous beam. Here is a hinge support, here is a one roller support, and here is a one fixed support. So this is an example of continuous beam as it contains number of supports more than 2. Free body diagram for this beam can be drawn as AX, this is AY, here is a vertical reaction BY. For fixed support, 3 number of reaction will be generated, that is CX, CY and moment in C support. So this is all are types of beam. Next point is types of load. So in mechanics there are some types of load we can use to analyze any body or support. So first type of load is concentrated load. If load is acting on very small area, then it is considered as concentrated load. We can call it also as point load. If intensity of load is acting at a point or very small area, then such a type of load is called as a concentrated load. Concentrated load is normally shown by arrow. So this is what a concentrated load acting at point P having magnitude P Newton or P kilonewton. So this is a what magnitude or intensity of point load. This is what point of application. Normally unit used to show point load or concentrated load is Newton or kilonewton. Okay. Next type of load is uniformly distributed load. In short, we can call it as UDL, uniformly distributed load. So let's see one example of uniformly distributed load. Let's see, here is a one beam AB and it is totally loaded by uniformly distributed load. Okay. So what is mean uniformly distributed load? If intensity of load on particular length of beam is totally distributed with same effect or same action, then it is called as uniformly distributed load. Its distribution over some length is equal, then it is called as uniformly distributed load. Normally it is shown by this sign, or sometimes this sign will be used to show uniformly distributed distributed load. Okay, let's see. This one example. The beam AB is totally loaded by uniformly distributed load having load intensity W Newton per meter. Okay, so here is one example of beam. Beam AB is loaded with uniformly distributed load W Newton per meter. So normally unit used to show uniformly distributed load is Newton per meter or kilonewton per meter. How much quantity or how much amount of load is acting per meter is for uniformly distributed load. During analysis of any body or beam, always uniformly distributed load is converted into point load. So during conversion, converted point load's magnitude can be taken as area of this portion. So, and point of application can be taken as centroidal portion for this beam. So magnitude for converted point load will be area of this. Let's consider L will be length of beam. So area for this beam will be W into L. So converted concentrated load's magnitude will be WL and it will be at a distance of L by 2 from support A as well as support B, because centroid of this portion will be at center. So converted point load beam diagram will be like this. This will be converted concentrated load having magnitude WL. Now unit will take as Newton and it will be at a distance of L by 2. Okay. Same procedure will be do for this beam. Take area of this. So W into L will be area. This is a magnitude and will be at a distance of L by 2. So this is what uniformly distributed load. Now our next term is statically determinate beam and statically indeterminate beam. So what is mean statically determinate beam and statically indeterminate beam? We know that in engineering mechanics and in that chapter, our unit equilibrium, we use three conditions of equilibrium, that is summation f of x is equal to 0, summation f of y is equal to 0 and summation m is equal to 0. So there are three conditions of equilibrium. Now, during analysis of any beam, there are some unknown reactions and these equilibrium conditions are used to find out the magnitude of unknown reactions. If particular beam we able to analyze by using three equilibrium conditions, then such a beam is called as statically determinate beam. If all unknown reactions are found out by using our three equilibrium condition, then such a beam is called as statically determinate beam. If beam is having some unknown reactions and we are not able to find out magnitude of all unknown reaction by using our three equilibrium condition, then such a beam is called as statically indeterminate beam. So why this happen? When number of unknown reactions are less than or equal to our three equilibrium condition, then beam will be statically determinate beam. So that is what condition for statically determinate beam. beam will be statically determinate if and only if the beam is having number of unknown reaction equal to 3 or less than 3. What is 3? Number of equilibrium conditions. Then if unknown reactions or number of unknown reactions are greater than 3, then such a beam is called as statically indeterminate beam. The number of unknown reactions are more than 3. We can find out any 3 reactions magnitude, but remaining we will not find out by using 3 equilibrium condition. So such beam is called as statically indeterminate beam. The number of reaction which we cannot find out by using our 3 equilibrium condition, so this count is called as is indeterminacy. Let's see example. So first example we can take for simply supported beam. So for simply supported beam we can take example as simply support is having one end as hinge support and other as roller support. So draw free body diagram for this beam. As support is hinge support, number of restricted reaction will be 2, that is AY and AX. Here number of restricted reaction will be 1, that is BY. So number of unknown support reactions are 3 and our equilibrium conditions are also a 3. So our main condition, that is unknown reactions are equal to 3, is satisfied. So this beam is statically determinate beam. All unknown support reaction can be find out by using our 3 equilibrium condition. Now let's see example for statically indeterminate beam. So example for statically indeterminate beam, we can take a fixed beam. So for fixed beam, we can take one example that both ends are fixed at support A and B. Now draw its free body diagram. All 3 restricted support, all 3 reactions at support are restricted. That is AX, AY, and moment at support A. Here BY, BX, and moment in B support is also restricted. So number of unknown reactions are 3, but we are having only number of unknown reactions are 6, but we are having only 3 equilibrium conditions. So what happened here? Number of unknown reactions are greater than 3, that is our equilibrium condition. So this condition is satisfied here. Number of unknown reaction is greater than 3. So this is what example of statically indeterminate beam. In all these 3 reactions, we can find out magnitude of any 3 only, and remaining 3 we cannot find out its magnitude by using equilibrium condition. To find out remaining 3 reactions magnitude, we use some standard methods. So this is not your syllabus part. We are having only this much part, and remaining 3 reaction is nothing but its indeterminacy. Okay, so this is a statically determinate beam, statically indeterminate beam, and this is the standard condition that we can use to show whether the beam is statically determinate or indeterminate.